Module 5, Lecture A, Any All Callable. By the end of this lecture, you will be able to use any and all with iterables of booleans or predicates to express complex conditions succinctly. Combine any and all with generator expressions to avoid unnecessary intermediate collections. And use callable to check whether objects can be invoked and to guard dynamic function calls. Mastering any, finding true values. When working with collections, you often need to know if at least one element satisfies a condition. Instead of writing a manual loop and tracking a flag, you can use a built-in tool that scans the iterable and returns a single true or false value. It follows the language's usual rules for what counts as true, which makes the code easier to read and reason about. This approach simplifies your logic, reduces the chance of errors in control flow, and clearly expresses your intent in a single operation. In many programming languages, values such as numbers, strings, and collections can be treated as either true or false, where non-zero or non-empty values are usually true and zero or empty values are false. When you use this kind of tool with something you can loop over, it checks each element's truth value. If it finds at least one element that counts as true, it returns true. If none do, it returns false. This turns what might be a more complex check into a single, simple expression. When working with real-world data, you often need to know whether any item in a collection satisfies a certain condition. For example, you might check if any survey response chose a specific option or if any sensor reading is out of range. This kind of construct scans through the collection and stops as soon as it finds a match, using either explicit Boolean values or values treated as true or false. It lets your code closely match natural language questions, such as whether any payment failed or any transaction exceeds a risk limit, while keeping the logic concise and easy to reason about. Python code, finding true values. In this lesson, we show how the any function can quickly check if at least one value in a simple collection is true. Instead of writing a manual loop to look for a successful case, you can rely on this built-in tool to do the work for you. We use everyday examples, such as checking test results or sensor readings, to illustrate how any reports whether there is at least one positive or active value. The focus is on understanding how this function simplifies common checks and produces clear, easy-to-interpret outcomes. We create a list of 4 true or false values, where each value represents whether a test passed or failed. True means the test was successful, and false means it failed. Our goal is to find out if at least one test passed. This setup lets us later use a built-in function that checks whether any value in the list is true, making it easy to see if there is at least one successful test result. The any function is used to quickly check whether at least one test in a list has passed. Instead of writing a manual loop and using a separate flag to track success, you can rely on this built-in function. It goes through each test result and returns true as soon as it finds one that is true. In other words, it directly answers whether there is at least one passing test in the collection. we display a message that shows both the list of test results and whether any test passed. Using a formatted string lets us insert these values directly into the message so it is easy to read. This output confirms that at least one test was successful because the overall result is true. We have a list of temperature readings in degrees Fahrenheit, where each value represents the temperature in a different room. Our goal is to find out if any room is uncomfortably warm, which we define as having a temperature higher than 75 degrees. Instead of relying on the fact that non-zero numbers are treated as true in Python, we explicitly check whether each reading is greater than 75. This clear condition lets us accurately identify which rooms are too warm. We use a list comprehension to check each temperature reading and see if it is greater than 75 degrees. This produces a list of true or false values, where true means the room is too warm and false means it is not. Doing this in one line is efficient and prepares the results so they can be quickly analyzed using the any function. We use a built-in function that checks a list of true or false values to see if any room is too warm. It returns true when at least one value in the list is true, meaning at least one room is above the warm threshold. This replaces a longer manual loop that would need extra logic to stop early. As a result, the code is shorter, clearer, and its intent is easier to understand. We display the list of temperature readings, the matching true or false values that mark which rooms are too warm, and a final summary stating whether any room is too warm. This shows how numeric temperature data is converted into Boolean values and then combined into a single truth value. Using the any function on these Booleans clearly tells us if at least one room exceeds the comfortable temperature threshold, demonstrating its practical use with real-world data. This script shows how to use the any function to quickly check whether at least one value in a collection is true. It first looks at a list of test results, where each entry indicates if a test passed, and uses the any function to confirm that at least one test was successful. It then examines a list of room temperature readings, turns them into true or false values based on whether each room is too warm, and again uses the any function to see if any room exceeds the comfort limit. The script prints the original data, the true or false flags, and a brief summary, highlighting how this function simplifies checking for at least one true value in a group. Short-circuit logic. Short-circuit logic means a sequence of truth values is checked from left to right, and evaluation stops as soon as a true value is found. At that point, the function already knows the overall condition is satisfied, so it does not need to examine the remaining values. This behavior is like asking a series of yes or no questions and stopping once you get a yes. The key idea is that evaluation ends as soon as the outcome is clear. Short-circuit logic lets a program stop evaluating conditions as soon as the outcome is clear, which saves time and resources. For example, when checking if a user qualifies for an offer, you should perform quick checks like age first and only call expensive external services if needed. In monitoring sensor data, you can stop processing as soon as a critical fault is detected, matching the urgency of real-world failures. Overall, this approach improves efficiency by avoiding unnecessary work. Short-circuit logic affects side effects and safety because not every condition in a combined test is evaluated. If some checks might cause errors or trigger network calls, you should place a simple, safe check first. When this initial condition fails, evaluation stops and the risky operations are never run. By ordering your conditions this way, you can prevent unnecessary work and make your code safer and more predictable. Python code, short-circuit logic. Demonstrate short-circuit behavior using simple predicate functions to show how condition evaluation can stop early. Emphasize that if an early check in a compound condition already determines the result, later and more expensive checks may never run. Use this to highlight why the order of conditions matters, both for performance and for safety. Placing cheaper or safer checks first can make the overall evaluation more efficient and prevent unnecessary or risky operations from being executed. The script starts by importing the time module, which provides functions for working with time. In this example, it is used to pause the program briefly, simulating a slow or expensive operation. This artificial delay helps illustrate short-circuit logic by making it clear when certain checks are skipped, since the program will only wait when those time-consuming operations are actually executed. This function checks whether a user is an adult based on their age. It first prints a short message to indicate that an age check is happening, which can help with debugging or understanding the program's flow. Then it tests if the user's age is at least 18. If the age meets or exceeds this value, it returns true, meaning the user is considered an adult. Otherwise, it returns false. This makes it a simple and efficient first step in decision-making processes that depend on age. This function, called medium check is premium, verifies whether a user is a premium member. It begins by printing a message to show that the premium membership check is running. It then converts the membership flag into a Boolean value so that any truthy input becomes true and any falsy input becomes false. Finally, it returns this Boolean result, indicating whether the user is treated as a premium member based on the given flag. This function simulates an expensive check on a user's purchase history. It first prints a message to show that the check is starting, then pauses briefly using a time delay to mimic a real remote lookup. After the pause, it returns a true or false value based on whether the user's name begins with the prefix VIP underscore, which represents a special status or membership. We set the user's age to 25 to indicate they are an adult, then specify that they are not a premium member, and finally assign their name as VIP underscore Alex, which suggests a special status based on the name prefix. We begin by announcing that we are evaluating conditions with efficient ordering, then use a function that returns true if any of several checks succeed and stops as soon as one is true. To keep this efficient, we first run a cheap check that uses the user's age to see if they are an adult. If that fails, we run a medium cost check that looks at their membership status to see if they are a premium member. Only if both of those fail do we run the expensive check that examines their remote purchase history using their name. By ordering the checks from cheapest to most expensive, we minimize unnecessary computation while still correctly evaluating the conditions. This code prints the result of a set of conditions that are checked in an efficient order. It reports whether any of the checks passed without doing extra work. The final outcome is stored in a variable that reflects these ordered checks. Because short-circuit logic is used, once an earlier condition is true, the remaining checks are skipped, which saves processing time and resources. We demonstrate how the order of condition checks affects performance by first announcing that we are using an inefficient sequence. We then evaluate several conditions with a function that returns true if any one of them is true. The first check is a simulated expensive remote history lookup that pauses briefly and tests whether the user's name starts with the letters VIP. After that, we perform a medium cost check to see if the user is a premium member. And finally, a quick check to see if the user is an adult. By putting the most expensive check first, it always runs even when a cheaper check could have stopped the evaluation earlier, clearly illustrating inefficient ordering of conditions. This code evaluates a series of conditions in an inefficient order, starting with the most expensive check, then a medium one, and finally the cheapest. Because of this ordering, it fails to take full advantage of short-circuit logic, where a true result from an earlier, cheaper check could skip later, more costly checks. The final outcome of this wasteful evaluation is stored in a variable and then printed, highlighting how the chosen order of conditions affects performance. This example shows how short-circuit logic and the order of conditions affect performance when checking if a user qualifies. In the efficient version, the program first performs a quick age check, then a membership check, and only if needed does it run a slow remote history check. Because the early checks pass, the expensive check is skipped, yet the result is still true. In the wasteful version, the slow check runs first every time, followed by the others, which causes unnecessary processing, even though the final result is the same. The main lesson is to order conditions from least to most expensive, so short-circuit evaluation can save time. Generator-powered any. When you combine checking for a true value with generating values on demand, you get an efficient pattern. Instead of creating a full list of true or false results, the function takes values one at a time from a generator, only when needed. This is especially useful for expensive checks, such as validating large datasets or evaluating complex conditions. It reduces memory and computation costs while clearly expressing that you only care whether at least one condition is true. Using a generator with a function is powerful because it uses lazy evaluation, stopping as soon as it finds a true result. This means the system only checks as many items as needed, such as scanning log entries until a critical error appears. The same idea applies to tasks like detecting late assignments or fraud in transactions. In each case, the process ends immediately when a positive match is found, saving both time and memory. Using a generator together with a separate checking function helps keep your code clean and flexible. The generator focuses on retrieving or streaming data from sources like files or web services, while the function only decides whether a condition is met. This clear separation makes the logic easier to understand and lets you change data sources without rewriting the checks. It also supports better performance and clarity as your data and the complexity of your conditions grow. Python code. Generator-powered any. This section focuses on using generator-based checks to handle expensive conditions efficiently. It highlights how generators enable lazy evaluation, so the checking process stops as soon as the first successful match is found, instead of evaluating every condition. You should also compare this approach with list-based checks, which typically evaluate all conditions up front, to see more clearly how generators can save time and resources in such scenarios. The script starts by importing the time module, which provides functions for working with time. In this case, it is used to create delays that imitate the time needed to read temperatures from remote sensors. By calling the sleep function, the program pauses for a set duration. This makes the simulated sensor data retrieval feel more realistic. This function simulates temperature readings from several distant sensors by looping through a list of preset temperature values. For each value, it announces which sensor is being checked, imitating a real sensor readout. It then briefly pauses to mimic the delay of an actual measurement. After the pause, it yields each temperature one at a time, making it work like a generator that supports lazy evaluation. We first collect all temperature readings from the sensor generator into a list, which forces the generator to produce every value right away. Then we use a built-in check to see if any of these temperatures go over 100 degrees, which returns true if at least one reading is too high. Finally, we print whether any sensor reported an excessive temperature. This method works, but it can be inefficient because it evaluates every temperature before deciding, even if an earlier reading was already above the limit. We use a generator expression to check sensor temperatures one by one only when needed, instead of processing them all at once. Then, we pass this generator to the any function to see if at least one temperature is above 100 degrees. The any function stops as soon as it finds a temperature that is too high, which makes the check efficient. Finally, we print whether any sensor reported a hot temperature. This script compares list-based and generator-based evaluation when checking sensor temperatures. It simulates slow temperature readings, then first uses a list comprehension to collect all readings before testing whether any exceed 100 degrees, which forces every sensor to be checked. It then repeats the task with a generator expression that evaluates readings one by one and stops as soon as it finds a temperature over 100. As a result, the list approach always processes all sensors, while the generator can stop early, illustrating the efficiency of lazy evaluation. All with generators, validating all constraints. To check that every item in a collection follows certain rules, it is efficient and clear to use a generator expression with a universal check. This approach lets you validate all constraints at once, without building temporary lists or other data structures. For example, when processing user registrations, you can confirm that each record has a non-empty name, a valid email, and a suitable age in a single pass. The generator produces each true or false value only when needed and feeds it directly into the overall check, so your code stays focused on the validation logic instead of managing intermediate results. When validating financial transactions, it is effective to use several small, independent checks that can be evaluated one at a time. For example, a transaction might need to stay under a limit, come from an active account, go to a destination that is not restricted, and occur during business hours. By combining these checks with a generator-style evaluation, you can quickly see if all conditions are met without building a full list of results. This on-the-fly processing is especially useful for large datasets or memory-constrained systems. Using a generator-style check that tests all rules is a scalable way to validate data as your constraints evolve. In a data quality pipeline, you might begin with simple checks, such as verifying sensor values are within a physical range and timestamps exist. Later, you can add more advanced rules, like detecting abrupt changes or comparing readings with neighboring sensors, without changing the overall structure of the code. This keeps the validation logic easy to maintain, efficient, and focused on ensuring that all constraints are satisfied without creating unnecessary intermediate data. Python code, validating all constraints. This section shows how to validate data by using the all function together with generator expressions. The goal is to check each user record against several simple validation rules at once. By using a generator expression inside the all function, you can test every constraint efficiently without creating temporary lists. This approach keeps the code concise, readable, and memory efficient, while still enforcing all required checks. The code first imports the data classes module, which lets us define simple data holding classes that automatically get common methods like initialization and string representation. It also imports the list and callable types from the typing module. List is used to indicate that a variable will contain a list of items, and callable is used to show that a variable will store a function or method that can be called with certain arguments. Together, these imports provide tools for structured data and clear type hints in the rest of the code. This code defines a data class called user record that represents a user with a name and email and an age in years. By using the data class decorator, Python automatically creates common methods, such as the initializer and the string representation. This reduces boilerplate code and makes it easier to create, view, and manage user records. Overall, it provides an efficient way to handle structured user data in a program. This function checks whether a user's name field is truly filled in. It takes a user record and returns a true or false value. Inside, it removes any spaces at the beginning or end of the name, then converts the result to a Boolean. The outcome is true if any characters remain after trimming, and false if the name is empty or only spaces. This ensures the name is not just blank or white space. This function checks whether a user's email address has a valid basic format. It looks at the user record and verifies that the email contains both an @ symbol and a period. If both are present, it returns true, indicating the email is likely structured correctly. This simple check helps ensure the email can be used reliably for communication. This function checks whether a user's age falls within an acceptable range. It takes a user record as input and returns true only if the age is between 18 and 120, including both limits. By doing this, it ensures that only users with a reasonable age are treated as valid. We create a list of validation rules made up of functions that each take a user record and return true or false. One rule checks that the user's name is not empty. Another checks that the email includes an @ symbol and a dot. And a third checks that the age is between 18 and 120. Together, these functions define the conditions a user record must meet to be considered valid. We begin with a list of user records, where each record is an instance of the user record class that stores information about a single user. In this example, the list contains 2 users, Alice, whose email is set to a version of alice@example.com and whose age is 30, and Bob, whose email is a version of bob@example.com and whose age is 25. This list will later be used to check each user's information against a set of predefined validation rules. We go through each user in the list and check whether they satisfy all the validation rules. To do this, we use a function that returns true only if every rule applied to that user is true. If every rule passes, the user is considered valid. We then print a message that includes the user's name and whether they passed all the validation checks. This script uses Python data classes and generator expressions to validate user records against a set of rules. Each user has a name, an email, and an age, and there are 3 checks. The name must not be empty. The email must contain an @ symbol and a dot, and the age must be between 18 and 120. These validation functions are stored together and applied to each user to see if all conditions are satisfied. The script then prints whether each user passes all the checks, with Alice passing and Bob failing because his email format is invalid. Short circuit evaluation. When you use a universal check with a generator expression, short circuit evaluation means the process stops as soon as the final result is known. If you are checking that every item meets a condition and one item fails, there is no need to examine the rest, because the overall condition cannot be satisfied. This is similar to finding one damaged item in a shipment and immediately knowing the shipment is not fully intact. The generator expression makes this efficient by producing values one at a time only when needed, instead of creating a complete list in advance. Short-circuit behavior is important for both performance and memory efficiency, especially when working with large or unbounded data. It allows a process to stop as soon as a decisive condition is met, such as ending a sensor validation as soon as the first out-of-range reading is found. This means the system avoids unnecessary work on the remaining data. The same idea applies when scanning large files or validating many database records, where values are generated only as needed and checking can stop early once a conclusion is reached. Short-circuit evaluation supports a declarative style of validation, where you simply state the conditions each element must satisfy and let the overall check control the flow. This makes your code read more like natural language, such as requiring every form field to be filled or each step in a workflow to succeed. Because generator expressions are evaluated lazily, this pattern also works well with expensive data sources, keeping the logic efficient and avoiding unnecessary processing while remaining clear and easy to follow. Python code, short-circuit evaluation. Explain how generator short-circuit behavior works by showing that once a condition fails, the generator stops and no further values are produced. Emphasize that this early stop prevents additional generator work and computation. Then contrast this with a full manual loop that continues processing all values, even when the stopping condition has already been met. Highlight that the key difference is how early termination in the generator saves effort compared with completing the entire loop. The script starts by importing the time module so it can pause execution for a short period inside the generator function. This delay simulates slow data production, making it easier to observe how values are generated over time. By doing this, the example clearly demonstrates the short-circuit behavior of the all function when used with a generator, since you can see that evaluation stops early as soon as a condition fails. This description explains a generator function that produces numbers one at a time up to a given limit. For each number, it logs a message saying which number was produced, then pauses briefly using a short time delay. After the pause, it yields the current number so the caller can retrieve it. This pattern demonstrates how generators can create a sequence of values gradually, with logging and delays, to mimic a more complex or time-consuming process. We use this example to show how the all function works together with a generator. The generator slowly produces numbers from 0 up to 9, and for each one, the all function checks whether it is less than 5. As soon as a number does not meet this condition, the all function stops checking any further numbers, which demonstrates its short-circuit behavior. In the end, we print whether all the generated numbers were under 5 or not. We run a manual loop that always goes through all the numbers it receives, starting with a result value set to true. The loop processes numbers from 0 to 9 produced by a slow number generator. For each number, it checks whether the value is 5 or greater, and if so, it changes the result to false to show that not all numbers are less than 5. After the loop finishes, we print this final result, demonstrating that the loop continues to process every number even after it finds one that does not meet the condition. This script uses a generator to show how short-circuit evaluation works. The generator produces numbers one by one, and a built-in function checks whether all of them are less than 5. As soon as a number fails this test, the check stops, and the generator stops producing more values, and the final result is false. In contrast, a manual loop runs through every generated number up to the limit, still ending with false, but continuing to process and print all values, even after it has already found a number that is 5 or greater. Chaining multiple conditions. Using a universal quantifier pattern with a generator expression lets you combine multiple conditions into one streamlined check for each item. For example, when validating user records, you can require that every record has a non-empty name, a valid age, and a correctly formatted email in a single pass. This avoids creating temporary lists, keeps the code clear and focused, and ensures that all elements meet the required constraints efficiently. Using a generator to chain multiple conditions lets you handle growing sets of rules in a single, efficient pass over the data. In real situations like financial screening or quality control, you often start with a simple rule and later add checks for things like currency, time, or regulatory flags. If each rule required its own pass, you would end up with many loops and wasted work. A single generator that applies all conditions in sequence can stop as soon as one fails, reducing complexity and improving performance. Chaining conditions in a generator is not only about performance, it also improves abstraction and reuse. You can split validation into small, clear functions and then combine them in a generator expression that reads like a policy. For example, in a hiring system, separate checks for education, background, and assessments can be linked together so each candidate is validated in a concise and expressive way. This approach scales well as policies grow more complex, avoids cluttering your data, and makes it easier for others to understand how multiple conditions are applied to each item. Python code, chaining multiple conditions. Use the all function together with a generator expression to chain several conditions into one compact check. This lets you validate simple user records in a single step without building temporary lists in memory. Because all stops as soon as one condition fails, it also avoids running any remaining checks that are no longer necessary. This approach keeps validation code efficient, readable, and focused on only the conditions that matter. We define a list of user records where each user is stored as a dictionary containing their name, age, and email. In the example, Alice is 30 with a valid email, Bob is 17 with an incorrectly formatted email that is missing the @ symbol, and Carol is 45 with a properly formatted email. Organizing the data this way makes it easy to loop through the users later and run validation checks on their information. We use a helper function to check whether a user record is valid. It confirms that the name field is a non-empty string after trimming whitespace, that the age field is an integer between 18 and 65, and that the email field includes an @ symbol to suggest a proper email format. The function returns true only when all these conditions are met, allowing us to quickly validate user records. We use the all function to quickly check whether every user in a list meets the required conditions. It works with a generator that goes through each user and calls the isValidUser function to test the constraints. If every user passes, the all function returns true, meaning all users are valid. If it finds a user that fails, it stops immediately, which avoids unnecessary checks and makes the process more efficient. This code prints a message that tells you whether all user records passed the validation checks. It relies on a result value that comes from testing each user against a set of conditions. If every user meets these conditions, the message confirms that all users have passed. This gives you a quick overall view of the validation process and shows whether any records might need more attention. We use a list comprehension to find users who fail validation by reusing the existing validation function. For each user, we check whether they do not meet the required criteria. If they fail, we take their name and add it to a new list. This gives us an efficient way to focus only on users who do not satisfy all the conditions. This code identifies and prints the names of users who fail at least one validation rule. It uses a list comprehension to go through each user and apply the same validation function used elsewhere. Any user who does not meet all conditions is marked as invalid and added to a list. Finally, the program prints a message listing these invalid users, showing how the shared validation logic can be reused to find specific failures. This script checks a list of user records to see if each one meets basic validation rules. A helper function verifies that the name is a non-empty string, the age is between 18 and 65, and the email contains an @ symbol. Using a built-in function with a generator expression, it efficiently determines whether all users are valid without creating extra lists and stops checking as soon as a failure is found. The script then reports whether every user passed validation and also prints the names of users who failed any of the checks, reusing the same validation logic. Understanding callable objects. Identifying callable objects. Callable objects are elements in a program that you can activate using parentheses, such as functions that perform tasks when invoked. Many languages also let built-in operations, custom objects, and library tools behave as callables. Understanding which objects are callable helps you design flexible code that can respond to different situations at runtime. This awareness is key for managing dynamic behavior in your programs. When your code works with values that are not fully known in advance, it is important to check whether an object is callable. Configuration data or plugins from libraries are not always simple functions. They might be plain data or complex objects that cannot be called. By testing if something is callable before using it, you can distinguish between objects that perform actions and those that are just data. This lets your program safely decide whether to invoke the object or handle it as static information. You can think of a program as a toolkit that contains both passive tools like configuration data and active tools like functions or objects that perform actions. When you store these different tools together in a generic collection, you need a way to tell which ones can actually be executed. Checking whether an object is callable lets you decide if it should be run as an operation or treated as plain data. This distinction is important for building flexible, maintainable systems such as analytics workflows or automation rules, where you mix configuration with executable logic. Python code. Identifying callable objects. Use the callable built-in tool to check which objects in your program can be called like a function. This lets you distinguish between functions, methods, and plain data values because only callable objects can be safely invoked. By testing objects with this built-in before you try to run them, beginners can avoid errors and make better decisions when invoking things dynamically in their code. We define a function called miles to feet that takes a distance in miles as its input. Inside the function, we convert this distance to feet by multiplying the miles value by 5,280, since that is the number of feet in 1 mile. The function then returns the result, so it can be used whenever we need to convert a distance from miles to feet. We prepare a few different objects to show how they behave. First, we store the number 42 in a variable, which is just a data value and cannot be called. Next, we store the text "Hello World" in another variable, which is also just data. Finally, we assign a miles to feet function to a variable, and this one is callable, meaning we can invoke it with parentheses to make it run and perform its task. This part of the code shows how methods that belong to objects can be treated like callable objects. We use the upper method from a string, which converts all characters to uppercase. By assigning this upper method to another name, we store a reference to it so it can be called later. This illustrates that methods, like functions, can be accessed and invoked when needed. Assigning the built-in length function to a variable shows that built-in functions in Python are callable objects, just like functions you define yourself. This means you can store them in variables and invoke them through those variables. Using the length function in this way provides another example of a callable object that can be used to find the size of different data structures. We create a dictionary called items to group several different objects so we can easily loop over them later. Each entry uses a descriptive name as the key and stores the actual object as the value. The collection includes a number, a text string, a function that converts miles to feet, a method that turns text to uppercase, and the built-in length function. By keeping these varied objects together in one place, we can efficiently test which of them are callable in a systematic way. We loop through each entry in a dictionary of items, getting both the item's name and the object it refers to. For each object, we check whether it can be called like a function by using a built-in test that returns true if the object is callable. We then print the object's name along with this result. This lets us quickly see which objects in the collection can be used as functions or methods. This script shows how to use Python's callable function to check which objects can be invoked like functions. It defines a simple miles to feet converter function, then creates several different objects, including a number, a string, a user-defined function, a method taken from a string, and a built-in function such as the length function. These objects are stored together and tested one by one with the callable check. The output reveals that the user-defined function, the string method, and the built-in function are callable, while the plain number and text are not. This illustrates how callable helps you identify which objects in Python can be dynamically invoked. Callable classes and instances. In many programming languages, callable objects are not limited to functions. Classes and even their instances can also be called. A class is callable because using it creates new instances, much like using a factory. Instances can be designed to be callable as well, so you can use them like functions while they still carry their own data and behavior. This provides a simple call interface for interacting with objects. And when you check whether something is callable, both classes and these special instances usually report that they can be invoked with arguments. Callable objects are useful because they can store internal information while behaving like functions. For instance, a machine learning model can be called with new data to make predictions using its stored parameters, and a financial pricing object can be called with contract details to compute prices. In large systems, where objects are passed around dynamically, checking whether something is callable helps confirm that it supports the expected function-like interface. This makes the system more reliable and easier to manage. Callable classes and instances are important for building flexible systems because they let you safely check whether something can be invoked before you use it. In plugin architectures, for example, you might import a class from a configuration file and rely on its callability to create instances when needed. When working with third-party objects, testing if they are callable helps you decide whether to use them as they are, adapt them, or ignore them. This pattern is common in web frameworks, data pipelines, and simulations, where a consistent way to trigger behavior is essential. Overall, Ensuring callability helps prevent runtime errors and makes it easier to diagnose problems when non-callable objects are used incorrectly. Python code, callable classes, and instances. This material explains how to use callable classes and callable instances in a simple, practical way. It shows that you can design a class so its objects behave like functions, and then safely check whether an object is callable before invoking it dynamically. As a concrete example, it uses a model that remembers how many miles have been driven and uses that information to predict fuel usage. Together, these ideas illustrate both the mechanics of callables and a realistic use case for them in modeling behavior over time. We define a class called SimpleModel to represent a basic relationship between miles driven and fuel consumption. In this class, the initialization method sets up each new object with a specific miles per gallon value, which represents the vehicle's fuel efficiency. This value is stored inside the object so that each instance of SimpleModel remembers its own fuel efficiency. With this setup, the class can later use that stored value to calculate fuel usage based on how many miles are driven. This class defines a call method so that an object of the class can be used like a function. When you call the object and pass in the number of miles driven, it divides that value by the miles per gallon attribute. The result is the number of gallons used. This provides a quick way to estimate fuel usage from the miles driven. In this example, we first note that the SimpleModel class is callable in Python, meaning we can use it to create objects. We then create an instance of SimpleModel with a miles per gallon value of 25. Because the class defines a special call method, this instance can also be called like a function. Finally, we check and print whether the instance is callable, confirming that it can be used to run the operations defined in that call method. We begin by setting the distances for two trips, one of 50 miles and another of 120 miles. We then confirm that the model can be used like a function, meaning it is callable. Once this is verified, we input the miles for each trip into the model to obtain the gallons of fuel used. In this way, the model dynamically computes fuel consumption based on the distance driven for each trip. The code displays the miles driven and gallons of fuel used for the first trip, using values that were calculated earlier. It then repeats this process for the second trip, again using the previously computed miles and gallons. This output clearly shows the fuel consumption for each trip and illustrates how the callable model instance works in practice. We create a small list of different objects, including the model instance, a number, a string, and a class, to show how to check whether each one can be called like a function. We then loop through the list and, for each object, use the callable check to see if it is safe to invoke. If the object is callable, we print a message saying it is safe to call and show its type. If it is not callable, we print a message saying we are skipping it and again show its type. This simple process demonstrates how to safely handle objects that may or may not be callable and avoid runtime errors from trying to call something that cannot be invoked. This script illustrates how classes and their instances can be callable in Python. It defines a SimpleModel class that stores miles per gallon and lets you call an instance like a function to compute gallons used for a given number of miles. The code shows that the class itself is not callable in this way, but an instance is, because it defines a special call method. It then uses this instance to calculate fuel usage for 2 trips and prints the results. Finally, it loops over several different objects, checks whether each one is callable, and prints the outcome to demonstrate how callable checks help you safely decide which objects can be invoked like functions. Safe dynamic calls. In dynamic designs like plug-in systems or data-driven pipelines, you often need to work with objects that are not hard-coded, so you cannot safely assume they are functions. Before you try to execute such an object, you should first check whether it is actually callable. This callable check is especially important when objects come from external sources such as configuration files or third-party libraries, where you do not control their type. By verifying callability before invocation, you reduce runtime errors and make your code more robust against unexpected inputs. When using dynamic calls in your code, you must ensure that each step is actually callable to avoid crashes at runtime. For example, if a configuration for a web app accidentally includes a string or number where a function is expected, blindly calling it can cause failures during user requests. By checking whether each step can be called and handling errors gracefully, you can show clear error messages, fall back to safe behavior, or log warnings for invalid steps. This turns potential crashes into manageable issues, simplifies debugging, and improves the overall user experience. In advanced systems that allow external teams to register custom event handlers, such as fraud detection rules or content filters, it is critical to ensure that any dynamic call is safe. Before invoking these handlers, you must verify that they are actually callable and follow the expected interface. This reduces the risk of misconfigurations, malicious behavior, and failures caused by poorly written extensions. By consistently performing this check, you keep the environment stable while still allowing new functionality to be integrated and errors to be handled effectively. Python code, safe dynamic calls. When making dynamic calls to objects, always check first that the target is actually callable before you invoke it. Configuration values might be valid functions, but they can also be invalid, non-callable entries. Your code should detect this, safely call only the valid functions, and clearly report when an object has been called successfully or has been rejected because it is not callable. This approach prevents runtime errors and makes the behavior of your program easier to understand. This line brings in specific type tools from Python's typing module to support type hints. Any is used when a value can be of any type. Callable describes something that can be called, like a function or method, and dict represents a dictionary with defined key and value types. Using these types makes function definitions and data structures clearer, which helps keep the code more readable and maintainable. This function converts a distance measured in inches into feet. It takes one input, the number of inches, and returns the equivalent distance in feet. To do this, it divides the inches by 12 because there are 12 inches in 1 foot. This simple calculation helps standardize measurements when working with different units. This function, called shout message, takes one input called message, which should be a string. It converts the entire message to uppercase to create a shouting effect. After changing the letters, it adds an exclamation mark at the end to increase emphasis. Finally, it returns this modified version as a loud and clear form of the original message. We define a configuration dictionary that links text keys to different kinds of values. One key is associated with a function that converts inches to feet, and another key is linked to a function that turns a message into uppercase with an exclamation mark. A third key is intentionally mapped to a plain string that is not a function, representing an invalid handler. This setup shows how we can dynamically call functions based on configuration, while also safely handling entries that are not actually callable. The safe call function is designed to run an action only if it can actually be called. It accepts an action as its first input, plus any additional positional and keyword inputs. Inside, it checks whether the action is callable. If it is, the function executes the action with the given inputs and returns the result. If it is not callable, it prints a warning that a non-callable object was used and returns nothing. This helps avoid runtime errors caused by trying to call something that is not a valid function or callable object. The code first prints a message to the console to announce that the dictionary of configured actions is about to be used. This message introduces the upcoming demonstration of how to safely call functions that are stored in the dictionary. It draws attention to the available keys and the example function calls that follow, helping the listener understand what is being executed next. We use a helper called the safe call function with two inputs: the distance scaling action taken from the configured actions dictionary, and the number 36, which is the distance in inches. This scaling action is a function that converts inches to feet. The safe call function first checks that this action can be called, and since it can, it runs the conversion and returns the result. Finally, we print a message to the console stating that the scaled distance in feet is equal to this returned value. We begin by calling a helper function that safely invokes actions, passing it the notify user action from the configuration and the text package shipped. This helper checks whether the action can be called, and since it is linked to the shout message function, it runs that function. The shout message function converts the text to uppercase and adds an exclamation mark, producing package shipped. This transformed text is stored as the result message, and then a final line is printed to the console that shows the notification message, result followed by this processed message. We try to call the function associated with the bad handler entry in the configuration, but that entry actually holds a string, which cannot be called like a function. The safe call helper first checks whether the target is callable. Because it is not, the helper prints a warning that the call was skipped. As a result, the attempted call returns the value none, and this none value is then printed as the outcome of the bad handler safe call. This script shows how to safely make dynamic function calls by first checking whether an object can actually be called. It stores several configuration actions in a dictionary, where some entries are real functions and others are just values like strings. A helper function tries to run each action, but only executes it if it is callable. Otherwise, it prints a warning and returns none. In the valid cases, it correctly converts 36 inches to 3 feet and turns the message package shipped into the uppercase message package shipped. When it encounters a non-callable string, it simply skips running it, demonstrating robust and graceful error handling. In this lecture, you learned to use any and all with iterables of booleans or predicates to express complex conditions succinctly. Combine any and all with generator expressions to avoid unnecessary intermediate collections. And use callable to check whether objects can be invoked and to guard dynamic function calls. In the next lecture, Lecture B, we will go over sorted and reversed. Thank you for your attention. See you all in the next lecture.